My presentation today was looking at a replicated tile drainage study in Douglas County, and that's where we have 6 treatments with 3 replicates in both corn and soybean phases. There's 36 tiles that we're looking at on one farm. And with these 6 treatments that are based on nitrogen timing differences, timing of application differences, and also with and without a cover crop. I hope that I can make this point to everybody that tile nitrate is not simply a matter of excessive N fertilization. It's a lot more complicated than that. But, spoiler alert, timing of N application is important, and I'll get to that. So I'm going to feature an NREC project today that is entitled Nitrogen Management Systems in Tile Drain Fields, and we even have our aim or our goal in this title, and that's to optimize yields while minimizing nutrient loss, especially nitrate in tiles. It takes a lot of people to do this work, and I'd like to bring that to everyone's attention here. From the University of Illinois, we've got John Green as a field technician, Corey Mitchell, lab technician, 2 more technicians with us, Michelle Rolfe and Luis Andino. John Pike is helping with some cover crop specialty information. Nick Cedar is our entomologist, making sure that we don't end up with a different problem than what we started with, which is nutrient loss. We don't want to trade nutrient loss for pesticide problems, or pest problems, I should say. Emerson Nafziger helps us out. He's calculated my economic optimum N rates that I'm going to show. And then we have a multitude of undergraduates that work for us. And from IFCA, Illinois Fertilizer and Chemical Association. Couldn't do this work without Dan Schaefer and the help from Jason Solberg, and 2 participating farmers, which is Dick Searles and Eric Miller. And Eric also helps us do some custom work on this project, and I'm going to show some N-rate studies from Eric's farm as well. So I'm going to start with a look at the topography of Illinois. And the last glaciation, the Wisconsin glaciation, scoured and flattened the northern eastern half of our state. And this is the extent of that glaciation. And that's where most of our tile drainage is concentrated. And we also have this Grand Prairie region that left us with very high organic matter soils. It's also overlaps with the flat area. It extends outside the boundary of the glacial moraines due to those outwash areas. But those 2 combine to have formed some very productive soils. We just needed some drainage. So we put in ditches 125 or so years ago, and lots of tiles that lead to those ditches, and we've created some of the most fertile cropland in the world. I think of tile drainage as a prerequisite for high-yield environments. However, there is a side effect, and unfortunately, tile drainage water carries nitrate with it. Now, the first time I started looking at tile drainage was back in 1992. We had a constructed wetland project. I was the project manager, and that was right there at that red dot in the Embera River. And we began to sample the river there on a road at 300 North, and then soon realized we should be going down to Camargo, where the USGS gauges the flow, so we could determine the load. And so we've been going down to Camargo since '93. And we're sitting right here at the top of a moraine as we sit here today. And that divides the Salt Fork from the Embera River. We're actually in the Salt Fork, but 100 yards away is the Embera River, just down over the moraine. And that's the headwaters for this watershed. And it turns out it's a good watershed to look at nitrate loss because there's very few farm animals, so we don't have to sort out manure. It's 90% row crop ag. There's very little sewage effluent because Urbana-Champaign sewage effluent actually goes into the Salt Fork. So we don't have to subtract that out either. And it is an extensively tile-drained watershed. And from that early work, when we were looking at constructed wetlands to intercept tile drainage, and they worked quite nicely, by the way. A sidebar is that they removed 50% of the tile nitrate. So constructed wetlands can work nicely. We were sampling about 6 tiles on this farm, and we noticed just after 4 years of measuring tile nitrate that whenever the tile stopped flowing, which is those breaks in between all those dots, no samples to be taken, the river quickly goes down to below 1 part per million. So it was quite obvious that tiles were controlling river nitrate. But what stunned us was that we could just take this one tile and regress it against the pattern of nitrate in the river, and we get an R squared of 0.7. So how is it possible that just one tile located in the middle of this 119,000 acre watershed could match up so well with what we saw in the river? And it's because, well, first I must say is that tile is only looking at what comes out of corn and then what comes out of soybean, where the river integrates both crops at the same time. We have about an equal mixture of corn and soybean in this watershed. So how can that one tile that's not, it's out of sequence as far as a rotation with the river predict that river nitrate? And it's because we lose plenty of nitrogen after soybean. So there's not that much difference between N loss after corn and N loss after soybean. And I hope this presentation and this data today can shed some light on why we lose nitrogen after soybean. So the USGS uses the bridge there near Camargo as a weir structure, and so they're able to gauge the flow. We multiply by concentration and we get load, and since 1993 we've driven to that bridge 1,510 times. We know that bridge well, and we just hang a bucket off of that bridge and we get a sample, we plunge it down through the water column, and we bring that back and look at nitrogen, phosphorus, and a host of other things. And this is the river data since '93, and you can see when we regress river flow versus load, pounds of nitrogen going down the river, there's really quite a tight relationship. And you would expect that because flow is part of the load calculation. And on average, we get about 13 inches of the precipitation to turn into river flow. We get about 40 inches of rain here. So about 1/3 of precipitation turns into river flow. But if we take 13 up to this regression line and over, we're losing about 3 million pounds a year down that small stream. It's 25 miles from here, picking up that much nitrogen. And that equates to 27 pounds per acre per year. We have loss as high as 50 pounds per acre in a wet year and as little as 8 pounds per acre during dry years. And it's interesting to see that 2019 is still falling right on the line. Now, I've seen a lot of tile drainage go in this watershed in the last 27 years, and I think it's impressive just to see that we haven't gotten worse. If 2019 was trending above the line, that would suggest we're getting worse. But of course, our field nitrogen balances have gotten better, and we're more efficient with our fertilizer use, and we've had a lot of good crop years in a row. And so you would think that if the load was below the line, that would show we're improving water quality. So we're still on the line. Well, what about 2018? Still on the line. 2017, I could continue going back in time. But we're not seeing any trend either way. At least it's not getting worse, because we've certainly put in a lot of tile in the last 27 years. And we're putting it in on pattern systems as well. So if it's not all fertilizer that's ending up in the river, what could the other source be? Well, obviously it's soil and mineralization. And that's important to crops, but unfortunately it's probably important to a portion of the tile nitrate loss. So this is a process called N mineralization, and it's the decomposition of organic N. And simply defined, it's the process by which organic N is converted to plant-available inorganic forms, which is nitrate and ammonium. It's a microbially mediated process. That's bacteria, fungi. But when I say mineralization, I'm really talking about net mineralization. That's mineralization minus immobilization. And immobilization is where a microbe is eating some carbon-rich residue, like corn, nitrogen poor, and so for the requirement of the bacteria or the microbe itself, it needs more nitrogen. It's not getting enough from the feedstock. It's chewing up, and so it takes nitrate from the soil and actually makes it unavailable to the plant. That's called immobilization. So net mineralization is this tug-of-war between mineralization and immobilization. And often you'll see that a 25-to-1 carbon to nitrogen ratio is this cutoff. But I found a nuanced version of this in an old textbook, and I've been using it since I found it, that above 30-to-1, that would be net immobilization. But when you get residues that are lower than 15-to-1, like a red clover cover crop or something like that, then you would have net mineralization. And of course, these are microbially mediated processes, so weather can greatly influence and impact annual mineralization. And we had a perfect example in the years of 2017 and 2018 being back-to-back and extremely different winter and springs. 2017 was a very warm winter. We had temperatures well above the 30-year average, which is the red bars, in January and especially February. February is very warm, but also April was warm. And then, ironically, it got cold as soon as we planted the corn. But then in the next year, we have quite a cool winter, and more importantly, a very cold April, well below the 30-year average. And then we got extremely warm in May, and the crops took off. And so with these two very different years, you might think that mineralization would be different. And this is mineralization that's occurring outside the growing season, prior to our row crops being planted, and I think it's pretty important that we consider that. But nitrate's nitrate. It doesn't matter if it came from fertilizer or from mineralization, it can leach into tiles. So I moved to our NREC study that's done in Piatt County on Eric Miller's farm, and Emerson has provided this evaluation of economic optimum N rate, and that's the last increment where the cost of the fertilizer is offset by the increase in corn yield. And so you can see our economic optimum N rate following that warm winter was only 144 pounds per acre. But now following the cold winter, that cold April, well then we needed almost 200 pounds. Same soil type. Pretty impressive to think we could have a 55-pound per acre swing in available nitrogen due to mineralization, thanks to the difference in soil temperatures and air temperatures those 2 years. So it's just proof that, being a microbially mediated process, that weather can have a great impact, and we needed more nitrogen after that cold winter. So moving to our replicated tile drainage site in Douglas County to try and test ways of reducing tile nitrate loss with various systems. This is our setup where we have an agri-drain structure that intercepts the tile line itself so that we can get samples out. Automatic water samplers are there on tables, and everything is mouse-proofed because mice are a real problem. So the objective of this NREC study is to evaluate when and how tile nitrate losses occur in corn and soybean rotations. Well, we've got 5 years of data now, so I've got a good idea of when nitrate loss occurs to tiles, and I think I can shed some light on how. And some of our treatments will work with the timing of N application. We have a reduced rate as well. There's different sources because of the difference in timing. And then we have one treatment where we have a cover crop. And we have 6 treatments, and there's 3 replicates. And so there's 18 tiles that we're looking at. And then we have both phases of the rotation being monitored at the same time. So it takes 36 tile lines to accommodate this study. They're 100 feet apart. They're very long tiles, and each tile is about a 4-acre plot. So a very large plot for a replicated study. And it's randomized complete block design. We like strip till before corn, and that's Eric putting in strips in the fall, and then no-till soybean. And here's our field design and field map. We've got all these parallel laterals. Very rare to see long parallel laterals. This field is just perfect for us to conduct this kind of research. And then there's a ditch that runs through it, and so we've got 3 blocks that are in red. That's one crop. 3 blocks in blue, that's the other crop, and they're rotating back and forth every year. And then we overlay our 6 treatments, and they're randomized in each one of those blocks. And briefly, the 6 treatments are as well. We put all of the nitrogen on in the fall versus a 3-way split, half in the fall, 25% at planting, 25% side dress, and then all of the nitrogen in the spring, a 75% rate, where it's 120 pounds, 160 pounds our full rate. Then we have these 2 50-50 splits, where half applied in the spring and half side dress. It's an early side dress. And one has a cover crop and the other one doesn't. And here's a picture of the outline of one of our plots. They're large plots. This was a cereal rye plot that you can see give us the boundaries. And clearly, this lacustrine area is very flat and scoured by the glacier, and we need tiles. And so, since we need tiles, we've got to find a way to reduce nutrient loss. And here's the 6 treatments spelled out a little more. That full rate does get an inhibitor in the fall, and so does the half rate, where the full rate in the spring we don't put an inhibitor on. Probably could have used that one year, and I'll get to that. The reduced rate is also in the spring, no nitropyrin. And then these 2, like I said, it's a 50-50 split, where we're trying cereal rye after corn, ahead of soybean. And in the beginning, we didn't want something to overwinter in front of corn, and so we tried oat and radish. But I'm afraid that it's not growing enough to see us have an impact on tile nitrate loss. But here's the money graph. This graph has all 36 tiles in it, and we start out after 1 year. We had a setup year, and then so we start at the end of 2015, and we just say all treatments are starting at 0, and each day is added to the next day, and you can see all these squiggly lines. Those are events that are moving the load up quickly, and then we'll have a flat period. Well, there's no tile flow at that time. And then again the next year, and then no tile flow. And so you're seeing 3 years of cumulative load, and you can see the 6 treatments have separated very nicely, statistically different, and we're losing the most nitrogen with the fall end treatments, and the least when we have the 50-50 split with the cover crop. And it's a 41% decrease overall. But I circle these 2 because this is the loss from the full rate, but split equally, spring and side dress, versus a 75% rate all in the spring. So we've lost just as much nitrogen out of the 75% one as we did the full rate. And so timing matters, and it shows that tile nitrate is not simply a matter of excessive N fertilization. Just cutting back is not the answer, and that's the only treatment that gives us a yield hit. So we've lost yield by not putting enough N on, and we didn't reduce the tile load any more than we did if we just split it more in season and kept and not put any on in the fall. The other interesting thing is, though, there's no treatment differences among the other 5 treatments. So it doesn't matter that, at least for yield, that we lost more fall N than we did spring or side dress N. It did not hurt yield. And now why is that? It's like, are we over-fertilizing? No, we're not. It's mineralization probably makes up for the small amount of tile nitrate that we lose with fall N. So environmentally, it's not the best, but it's not hurting us as far as yield goes. So here's our soybean yields for the first 3 years, and they're they're all the same. There's no statistical difference. So you wouldn't expect there to be a difference. These N treatments are for corn, so there's no nitrogen on these soybean or added nitrogen. But what I want to point out here is that we're not hurting yield by having quite a bit of cereal rye growth ahead of soybean. So soybean can handle that higher seed end material and fix its own nitrogen and get around the potential of immobilization with cereal rye. Now here's looking at the 18 tiles that are soy corn, that part of the field. And there's 6 main colors here, and it's almost overwhelming. I recognize that, but so I'm going to highlight. There's the fall N in the first warm winter, separating from the other 12 tiles that didn't get N until the spring. So clearly a separation of tile loss due to fall N. The fall N treatments did remain higher the next year. But then with that cold winter of 2018, there's not as much spread between fall N and spring N. So again, there would be less nitrification of the anhydrous ammonia, and less of it got in the tile line. So weather is affecting fall N loss as well. Here's a very nice example of the cereal rye effect on tile nitrate. Each one of these dots is the average of the 3 replicates, and so these 3 tiles were just brought right down to about 1 part per million thanks to the cereal rye uptake, and it didn't hurt the soybean yield. Now we flip to the other half of the experiment, the other 18 tiles, and I am showing the setup year, which is 2015. We didn't get fall N on that year, nor did we have cover crops, so everything is spring N. And you can see if it rains after we put spring N on, we can have tile nitrate increase. But that first warm winter gave us a very dramatic effect of reducing tile nitrate with the cereal rye, and there was even a carryover benefit. If you drain the soil profile of nitrate, well, when the tile starts flowing again, it's still at that low value. I do not believe that is because of the oat and radish, and I'll have a picture of that here in a moment. But I want to point out that the green dots, which is the spring nitrogen in 2017, is right up there with the fall N. And it's because February of 2017 was extremely warm, and a lot of people put their anhydrous on in that month. So we decided to as well. We put it on February 28th. So our spring N is really a late winter N. And by protocol, we didn't have an inhibitor with that. And so maybe we should have put an inhibitor on. If you're putting your spring N on in the winter, maybe you ought to use an inhibitor. I'm not sure. I don't have the data to say that. But I think this together made spring N look about as leaky as fall N that year. Now here's what our cereal rye looked like. This is the cereal rye in the first year that we had it, that had that tremendous reduction in tile nitrate load. It's not very impressive looking, really. It's actually N deficient. You can see that it's a little yellow, and good biomass, but not a lot of nitrogen in that, and it has a wide seed-end ratio. So that's why we worry about cereal rye in front of corn. We're not so worried about it in front of soybean. In fact, we haven't seen a problem with it. But this cereal rye did lower the tile nitrate by about 10 pounds per acre that year. So that's a very significant drop. That was about a 45% decrease in tile nitrate loss in the very first year we tried it. That happens to be the number that we're trying to get to with the Illinois Nutrient Loss Reduction Strategy. Now here's what our oat and radish looked like ahead of corn. It's just not enough biomass to affect the tile nitrate loss. It's doing more than nothing, but I should have squat down farther, and if I'd have been lower when I took that picture, it might have looked greener and more impressive, but it's really just too sparse. And so in 2018, we switched to annual ryegrass, and the polar vortex that we had a year ago killed all of our annual ryegrass. And so two winter crops survived the polar vortex. That was cereal rye and winter wheat on Eric Miller's farm. So we are now trying winter wheat as our cover crop, and we'll terminate it just like we would a cover crop. So we've got that out there. Some bin run winter wheat out there. Very cost effective. So now I want to jump to the 2019 data. And I don't really want to talk about the crop year. I'd sort of like to forget about the 2019 crop year. It was a challenge for us, getting things planted. And in fact, we planted late and we put our spring N on quite late. But it gave us an opportunity to look at this tile nitrate data in a way that we just wouldn't have if we'd have been able to carry out the field work when we wanted to. So yes, fall N, it's not a good year for fall N. In fact, that's 55 pounds per acre of N loss compared to 31 lost in the spring. So N loss is up this year, and it's because of our late planting and our heavy June rains. We had very little uptake of the fertilizer by the time we had these big events in June. And again, this is the average of 3 reps. We hit 27 part per million coming out of our fall N plots. And so that's not what we desire, and so that's partly a product of planting late. But it's very interesting to see that when tile flow first started, which it started very early, we got very little reprieve this year from sampling tiles, the crop wasn't quite at physiological maturity. It was still probably taking up some soil nitrogen, and the first tile nitrate samples were very low. So showing you that soybean does a great job of scavenging soil N. And so there was nothing out there to leach at first, but then everything increases. Of course, the fall N is in there, and that confounds it. So I'm going to pull this, some main treatments apart here right after this. But here was the most surprising thing we saw, is how low the tile nitrate was following corn in 2018. And it stayed low. It started low just like coming out of the soybean plots at less than 1 part per million, but it stayed below 2 part per million all winter long, and then it did increase a little bit up to 3 to 5 part per million by the end of the drainage season. But this was astonishingly low tile nitrate coming out of corn. I've never seen anything like that in the 25 years that I have been looking at tile drainage water. And so what's going on here? I'm going to pull out the fall N treatments. They're not in this graph. I'll take out the cover crop treatment. It's not in here. And so we're just going to look at the 3 treatments that get spring nitrogen. And we didn't put any nitrogen on until May 21st, and that's where I cut this graph off. So we're not confounded by fertilizer at all. And this is a close-up then of the difference in tile nitrate coming out of soybean versus out of corn this past year. And I would have thought that in the other years when we put our nitrogen on at a normal time, like April or May, or even March or April, that these increases in tile nitrate would have been associated with the fertilizer. And I wouldn't be able to sort that out. But the weather gave us this view of what is the effect of the previous crop on tile nitrate without any other factors. And it's really surprising to see it go up quite that much. And in fact, we lost 4 times more nitrogen from the soybean plots than we did the corn plots that year. And both of these values here, these amounts, are just about 50% of the total tile loss. That means half of the nitrogen that got in the tile came from mineralization. So to take this a step further, why do I think the tile nitrate's so low after corn? We know that corn residue has a wide seed-end ratio normally anyway, so there would be immobilization potential following corn. But the 2018 crop year was lean. We were lean as far as the MRTN. We were on the low end, purposely on the low end. MRTN right now is about 180 pounds per acre. We were putting 160 on. And then a lack of mineralization in 2018 gave us a crop that was very efficient, but had a very wide seed-end ratio. And more evidence of this is that all of our stock nitrate plots were very N deficient. So at the end of the season, every plot showed extreme N deficiency. Decent yields, 205 bushel per acre corn, but not much N in that material. So I think the microbes that were breaking down all of this material immobilized the nitrate, kept it out of the tile. So proof of concept that we have, if we worked on the lean side of the MRTN, we might make a residue that's nitrogen poor, and it leads to greater immobilization during the wintertime and less tile nitrate. But then the reverse, where does all this nitrate come from after soybean? And these were high-yielding soybeans in 2018, had 80 bushel per acre, some of the finest soybean I've seen. And so if you think about mineralization following soybean, we used to call this the soybean N credit. And that's really a misnomer. It's more like a continuous corn penalty. But what was the essence of the soybean N credit? Well, there was more nitrogen available after soybean than after corn. Clearly a difference in net mineralization. But the soybean N credit would be less reliable because you don't know how much of that might leach. So we don't use the soybean N credit anymore in our calculations for N fertilization. We use MRTN, and it was a misnomer anyway. But I think this is getting at the soybean N credit. Now, if you're in a corn, soybean, wheat rotation, you probably more reliably use that nitrogen that is mineralized after soybean. This is a potential credit, but it's not really a credit because soybean removes more nitrogen with the grain than is fixed. So it's not truly a credit at all. It's more of a rotation effect. But what is the source of the nitrogen then that makes up this rotation effect? I don't think it's the soybean leaves. The soybean leaves were 22 to 1. We just got that data back. And the stalks were 60 to 1. But there's a lot less residue there than corn. So I think it's a difference of quantity and quality of residue that leads to this difference in net mineralization. And I think we're carbon limited after soybean. The soil is carbon limited. Maybe the population of bacteria dies off and there's a flush of release. But some of this nitrate can get in the tile. Anyway, so a summary overall is that fall N is leakier than spring N, and fall N has led to about a loss of only 10% of the fertilizer, yet that represents about 30% of the annual tile load, yet no yield loss. So the economics of that situation is not going to solve itself. We're going to continue to use fall N, and we're going to be a little leakier, but we're probably not going to see any yield decrease unless it was an extreme year for N loss. So I think the seed-N ratio is the key as far as the residue, and corn residue promotes N immobilization, where mineralization following soybean can clearly add to tile nitrate loads. Again, I think quantity and quality of residue influences the N mineralization. And so I think we need to tie up this mineralized N that is occurring and forming during the non-growing season. And I think cover crops may be the best strategy. So I want to leave you with this. This is my last slide. And this is a map of the Midwest, and it's a temperature map. And it's that very warm February we had in 2017. And we were 12 degrees above normal in February of 2017. And that's the year where we needed less nitrogen to reach our economic optimum N rate, and the cover crop grew well. You know, everything points to lots of mineralization. So in 2016, we have record crop yields in the Midwest. In 2017, we have record crop yields, but sandwiched in between these two record yields is the largest hypoxic zone ever measured. So I'm worried that warm winters are slowly draining our ecological capital from the prairie. And I think we've got to be concerned about N loss following soybean, and that cover crop might be the best strategy. So I hope this presentation has at least led you to the idea that tile nitrate is not simply a matter of excessive N fertilization. It's much more complicated than that. And if nothing more, I'm here to explain that to people on the outside looking in who want to think that farmers are just over-applying. It's just a simple matter of just putting too much nitrogen on. That is not true, far more complicated than that. So I'll leave you with that. I thank you.